Sean bienvenidos al tercer día y último día del 13º Simposio Internacional de Ingeniería Civil y Administración de la Universidad Panamericana. A continuación, tendremos la conferencia que pronunciará el Dr. Mete Sozen, profesor distinguido del área de estructuras de la Universidad de Purdue en Indiana. Esta conferencia es traída a nosotros por ALBA Proyecto Estructural, patrocinador oficial del simposio.
ALBA es un grupo de personas, más que nada. Es un fuerte grupo de personas con una gran pasión por las estructuras. Cada uno de los ingenieros que estamos aquí desarrollando proyectos estructurales, nos encanta desde ir viendo la concepción de un proyecto estructural, cómo nace, cómo se vuelve el esqueleto de una obra arquitectónica, y más que nada esa es la raíz y es lo que le da fundamento a todo lo que nosotros hacemos en el día a día.
Existen 4 puntos que siempre son los que tomamos en cuenta para el desarrollo de un proyecto, que vienen siendo el acoplamiento arquitectónico, que queremos lograr con cada uno de los proyectos sin modificar la arquitectura del mismo y haciendo que lo estructural siempre vaya de la mano. Otro de los puntos es la seguridad. Siempre tratamos que el proyecto cumpla con todas las especificaciones que marcan las normas y reglamentos.
Todos nuestros proyectos cumplirán con los más altos estándares nacionales e internacionales de capacidad y de servicio.
Otro de los puntos es la viabilidad económica, siempre tratando de optimizar la estructura, que el cliente se lleve algo con muchísima calidad y que no represente un gasto excesivo en su bolsillo.
La relación entre lo que nosotros hacemos y el tiempo es básicamente la exactitud. Así como el tiempo es sumamente preciso, nosotros necesitamos desarrollar una precisión y una exactitud en todo lo que hacemos para que en todo momento el proceso de cálculo, análisis, diseño que lleva a un proyecto estructural tenga exactamente esa exactitud milimétrica que tendría cualquier reloj con el tiempo.
La entrega precisa de la información, en donde nosotros plasmamos todos nuestros diseños en planos y en la memoria de cálculo, que sean totalmente entendibles para los constructores y que traiga toda la información que ellos necesitan.
Para la presentación del Dr. Sozen, invitamos al Dr. Roberto Stark, distinguido profesor de la UNAM.
Buenas tardes. Quería decirles que para mí es un honor y orgullo poder presentar a profesor Mete Sozen. Realmente, si hay un hombre actualmente que podemos decir su nombre, es el nombre de Mete. Él realmente ha trabajado y ha influenciado al gremio de las estructuras en todo lo que respecta a estructuras de concreto. ¿Quién no ha oído del marco equivalente, el método directo, el método de estructura sustituta, que realmente después se volvió el método de diseño por desempeño? Entonces, realmente es una gran oportunidad que tienen ustedes de conocer a un verdadero profesor y a un verdadero ingeniero en esta parte de las estructuras. Sin más por el momento, porque no quiero interrumpir el tiempo, que creo que es más valioso que lo oigan, por favor, Mete, si puedes pasar a darnos la plática.
Primero, hay que decir que, ¿can you hear me? Lo siento mucho que no puedo expresarme en español. So I'm very sorry. It's a lack of culture. I am a Mediterranean and I should know Spanish. But I know very little Spanish. All I can do is order beer someplace or that's about it. So I apologize. And I thank you very much for coming here today to listen to me during the siesta hour. And let me tell you, we have at Purdue University now a huge school of engineering education. And we always wondered what it was that they taught. I mean, is it different to teach engineers versus literati? One day, one of them came to talk to us, and we asked him, what do you know? What is it that we should know? And he said, I know that engineering students do not listen more than 20 minutes. So I appreciate that you're going to listen to me for 20 minutes this hour. But I beg you to listen to me toward the middle of my talk. If you want to take a little nap, do it now, when I shall be talking about generalities, important generalities, but nevertheless generalities. But then I shall go talking about earthquakes and talk to you about a very simple method that I think you should all know, if you don't already know it. And during that time, please stay awake when I tell you I'm going to talk about the simple method. Afterwards, I was asked to talk about the unfortunate attack on the Pentagon and on the World Trade Center. And I want to tell you a few things that I learned when I was working for the US government on trying to figure out what had happened. You can still hear me, yes? Yes, back there, you can hear me? Very good. And I do want to thank the Monares brothers. I want to take time, she's not here. Anna is not here. I want to take Anna, I want to take Monica. I want to thank all of the advisory committee of the group who were kind enough to invite me here. And I'm delighted to be here. I should tell you that this is not my first trip to your town. In the 70s, I used to come here every year. And sincerely, my favorite place in the world is suddenly I'm nervous. I forget the name. Barra del Navidad. I love that place. And I'm sorry I don't have time to go there this time. But those of you who live here are very lucky to be living in a town like this with such beautiful people and with such beautiful weather. I truly envy you. And I'm sorry that I stayed here for less than a week. But let me try to tell you some of the generalities that I want to tell you. If I can only figure out what I'm supposed to do with this. One. Oh, this is the front part. Okay. Nada. Okay. Look, let me talk to you about something that you might think is trivial, but is not. It took me a long time to figure this out. But what is more important for an engineer of any kind? Should he or she know what he or she knows? Or, why isn't this working? There. Should he or she know what she doesn't know? You know, there's a very subtle difference in meaning. Should an engineer know what he or she knows, or should an engineer know what he or she doesn't know? And that's what I would like to argue for in your presence. I'm doing something wrong. Look, you may have heard of Socrates. He lived long ago in classical Greece. And he was the son of a sculptor, actually. And he himself was a soldier before he decided to think. And he says in his writings, or rather as Plato summarizes him, he says that he thinks the craftsmen know things that he doesn't know. This makes me nuts. Why am I having trouble with this? Is it me?
It was off.
It was off. Oh, God, yes, yes, yes. It was off. That's why it wasn't working. And he says, I went to talk to them, and he found out that he was not fooling himself. They knew a lot of things that he didn't know. But each one of them, because they knew a lot of things about what they knew, they were ignorant about things that they did not know. And I'll explain to you in greater detail later on. This is my Spanish, not very good. And he says that error, the fact that they thought they knew everything, made them handicapped, more or less. Their wisdom petered away. So I ask, shall I stay as I am and not know anything, essentially? Or shall I be like them and know well about something, but not know that there are things I do not know? Hey, you know, I cannot overemphasize that. You're all engineers. You all know a lot. But there are things you don't know. And it is much more important that you know the things you do not know. You know the boundaries of your knowledge than what you know, as opposed to a scientist. I'm sure I'm not making a lot of sense to you, but eventually I think I shall come through. Look, and this is not, I can't ascribe it to Socrates or to Plato, but think of your friends, and you'll find that there are, in general, two kinds of engineers. Those who observe and sort of repeat what they observe, and those who think. Unfortunately, most of them will think but not look. I can give you hundreds of examples. And some will look but not think. Hey, but what you must try and do is think and also look. I mean, make an analysis, but make sure that the analysis is relevant to what it is that you're analyzing. I shall try to give you examples. But allow me to repeat, please, at the risk of being boring. Don't be one of those guys or gals who simply thinks and doesn't look at what it is that he or she is building. Or don't be one of those who simply looks and repeats what he or she has seen without thinking how to project it to other cases. I cannot overemphasize that, and I feel because of my lack of Spanish, maybe I'm not coming across to you, but I will try to. Look, it was in mid-18th century that we started thinking about building, because until then, we built by putting stone and stone. You know, in the Middle Ages, it was very important to build cathedrals in France and in Italy. And everybody was trying to reach that whatever it is up there. And as they kept building higher and higher cathedrals, in Beauvais, suddenly it collapsed. And then they stopped. They didn't go any further. Well, that's observing. That's learning from observation. That's looking. But they hadn't yet thought. It was in Italy that when they started seeing cracks in the dome of St. Peter's Basilica, that two of they called clowns in the Doge's palace decided to use analysis to figure out what was going on. You know, what was going on is something you can probably understand from that exciting competition that we saw today. When you build an arch, it tends to spread out. And that's what this was doing, and that's what they were having cracks along the sides. And they used what one would call the virtual work analysis. But allow me to take a side issue at the moment. You're familiar with Archimedes, right? You've heard of him. This is the guy who ran out of a bathhouse naked, an exhibitionist. Anyway, and he also found the lever law, the law of the levers. And if you have a lever like this, and if this side is 1, and this side is 5, then you know that if you put 5 there, you can keep it in equilibrium with 1 over there. And what do we normally think? Because 5 times 1 equals 5 times 1, right? Equilibrium. But the Italian clowns did their work through virtual work. And if I do the same problem through virtual work, I let the rod rotate, and if that distance is 1, and if this distance is 5, then the deflection there is 1, and the deflection there is 5. So if you put a load of 5 there, it'll balance a load of 1 over there. The work done simply being the force times the distance that you go through. You know, it's the most beautiful theory, I think, in the practice of engineering, I think, virtual work. And the Italians came up with it. Now, this is a puzzle for you, at least for those of you who haven't seen it, so pay attention. Let's see if anybody will be able to figure it out. If I have 2 beams with hinges at each end, supported simply. How do you say that in Spanish? Simple. Supported simply. And if we put a load over here, and if we put a load over here, do you understand that? This is free to rotate, okay? If this distance is 2, and if this distance is 1, if I put 1 kilogram force over here, what do I need over there in order to keep it in balance? 4? 2? ¿Qué prefiere? 2? Do you vote for 2? Yes, you got 1 supporter, only 1, and the others aren't 3, so 4. Hey, you win. But listen, think of it in terms of virtual work. Now think, that's difficult to think, but think. If I move this down 1, how much does that go up? Correct or no? I think if I move this down 1, that goes up 1. Doesn't it? Because these simply rotate like this, and that side goes up as much as this side comes down. No? Yes? Yes? I mean, if it's no, I've been kidding myself for many years. Now, if that is so, then to keep 1 kilogram force up there in balance, I need 1 kilogram force on that side. Correct? I mean, I admire the intelligence of the Italian, well, they call them clowns because they were clowns of His Majesty, the Doge. But it's a beautiful method. And if you try to do it through Archimedes, it's confusing. But if you think of it in terms of virtual work, it's easy. And surely some of you use it when you do limit analysis, the virtual work method. Any objections to this being, the question mark being 1 kilogram force? Does it seem odd to you? But of course, you know, there are... Who did that? Juan, ¿qué pasa? Did I do it? Well, I'll continue without slides. Is that it? Why not? And it would happen at the most exciting part of my presentation. I did it? Oh, something is happening. The computer is running out of, but something happened to the computer. You know, lately I've been trying to work with Windows 8. Let me give you one word of advice. Don't go to Windows 8. That's Well, I'll start from the beginning. No, but did you understand what I meant by it's more important that you know what you don't know than you know what you know in the practice of engineering? You see, unfortunately, too many of us, like the Socratic craftsmen, they know a lot about this, but they don't realize they don't know that. And sometimes it leads to problems. And I'll give you a few examples. Hey, I got a computer. Would you like that? Listen, let me get ahead of my talk, and I can pick up the slides later. I want to tell you an anecdote. I think it was in the either late 60s or early 70s. I was having dinner with Dr. Rosenbluth and Dr. Newmark in Boston at a meeting of the Earthquake Engineering Research Institute. And they were arguing about the ground motion in Mexico City. You know, even though those two guys were the most brilliant people I've ever known, to talk about PGA in Mexico City is sort of irrelevant and funny, huh? Because it's not the PGA, it's the displacement demand that drives Mexico City. You know, everything that you talk about earthquakes is an exception with respect to Mexico City. It is its own place. It's more like sinusoidal ground motion. But anyway, They were talking about what it could be. And Emilio was saying he doubted that it would go over 14% of G. And Nate, who was a conservative, was saying, hey, it could be almost 25%. Now, I heard this, and I made a mental note. And I usually believed Dr. Newmark more than anybody else. Now, in the year 1983, I was asked to make a study of the American embassy, the US embassy in Mexico City, to see if it was resistant to earthquakes, which I did. And of course, assuming even more that it was more like G over 3, like 33% of the acceleration of gravity. And I found it to be safe. It was okay. Now, in 1985, one day, I was giving a talk in Bogota, in Colombia, when suddenly 2 Marines appeared in the room, very much like this. And in their politeness, they shouted from the back, hey, are you Sozen? And I was talking, and I said, how could anybody be asking me if I'm Sozen while I'm talking? I said, yes, well, come over to the embassy right now. They said, what happened? Well, we have lost. They're talking about the Bogota embassy. We have lost the Mexico City embassy, and you are responsible. So they took me, they packed me onto a plane and sent me to Mexico City, as if it's going to make any difference. I'm not kidding. It's funny to talk about it now. I felt awful, and I was thinking, how am I going to kill myself? I didn't have a gun. I thought maybe I could buy some heroin, and then, seriously, and then jump out of a window. And are you satisfied that this is 1 kilogram? Think about this. This is really a very cute little balance that every engineer should be familiar with. Anyway, let's continue with this. Now, again, it was in early 20th century that the Italians started formal thinking for structural resistance. They said, we have to do something responsible. But do you realize that the earthquake that affected the mind of Western civilization most was the Lisbon earthquake of 1755, where thousands of people in churches were killed. And this seemed to be against, because just at that time, the British poet Pope had said, everything that is good, because the Lord makes everything. And Voltaire said, well, if the Lord is in charge, then how come he killed the people in the churches when he doesn't touch the people in the bordellos in Paris? And Rousseau, Jean-Jacques Rousseau, at that time said, that's right. God wants you to live in trees. If you had been living in trees, everything would be all right. But anyway, nothing intellectually was done, other than worrying about where the earthquake was coming from. Nobody thought about should we organize our defense. But the Messina earthquake of 1908, which killed 300,000 people, drove the Italians to think. These guys are smart. If you think about intellectual history of Europe, you'll find a lot of things came out of Italy. This was their idea. They said, they actually wrote that. They said, it's a dynamic problem, and you can't solve it statically. But we can fake it. We can make it look like it's a static problem. So they started talking about a force pushing a building laterally. And they didn't connect it to anything like ground motion or what have you. They said, if you're going to design, then you have gravity forces vertically, and you have earthquake forces laterally. And they said the lateral force, because they were talking about buildings that were 3 to 2 stories high, maybe 5 at the most. They said if you design for 1/8 or 1/12 of the weight of the building, it's good enough. Hey, can you follow me? I'm asking myself the question. I can speak slower if you wish. All right. But they said, we'll just assume there are lateral forces. And they really didn't care how it was distributed over the height because they were talking about low-rise houses. And they made that thing. It was the Californians who were smart enough to relate that to the, you know what I mean by PGA, right? The peak ground motion. And in the 1950s, the peak ground motion used to be 1/3 of the acceleration of gravity. And hey, that made sense. You could sort of translate it into a lateral force. In 1960, Professor Hausner of Caltech, who was a brilliant engineer, said the maximum is going to be 0.5. It can't be any more than that. In 1971, Hausner himself measured 1.25. Now it was getting serious. And in fact, I still remember the day when this was measured. We were all shocked. We couldn't believe it. Because now it was saying, well, you should design the building for almost its own weight. Didn't make any sense. By that time, we started getting smarter. Have you ever heard of a man by the name of Westergaard? Harold Westergaard? You know, in 1932, he wrote a paper, and he said, it's not the ground acceleration. It's the ground velocity that is important. And by that time, we were hearing that sound. So that when, in 2011, we measured 2.8 G. And you know, after this, the seismologists, who essentially control our life today by setting what the ground motion will be, said that we have done it scientifically. The ground motion cannot exceed 2 G. It's impossible because we know it from the properties of the rocks and the friction that you have. Well, we measured 2.8. And so help me, we could measure more than that. So suddenly, the Italian compromise, which was very clever, of designing buildings by assuming that there is a lateral force, doesn't work anymore. But look at our codes. What do they tell you? Huh? They tell you there are lateral forces, imaginary lateral forces. It's like taking dope, in a way. It doesn't seem correct. Look, now let me turn the page a little bit. And I would love it if you discuss this right now. If you don't agree with me, tell me it isn't so. But look, let me make the design, the analysis game, into the simple case where I have the exact structure, which happens to be a doghouse in this case. All right? Now, if I want to analyze it, I make an approximate model of the exact structure. And you can criticize me. You can say I should have this in 2 pieces. Yeah, but it is still approximate because how often do you analyze a building in 3 dimensions? How often do you analyze a building taking care of what the soil is doing? Whatever you do, this model that you use is approximate. And if you're awake, I see some of you sleeping. I love that. I'm used to it. You should ask yourself the question. Now, after I make the approximate model of the exact structure, then essentially I convert my approximate model to a linear spring, or elastic spring, if that is what you call it, and the mass. And then I make an exact analysis of it. Let me emphasize, I make an exact analysis of the approximate model. And do you believe it? Do you believe the results that you get? And you see, this is bad enough if you're dealing with gravity load, because with gravity load, sometimes you can tell what the load is closely is. But if you're dealing with ground motion, hey, do you know of any instance when we predicted the ground motion that occurred in a future earthquake? Do you know of any instance? And do you know of instances when we were totally wrong? So the demand that you put in here is not correct. We do it, we have to do it, but it is not correct. So it's more approximate than other types of analysis. So, and this is the point I want to make. Whenever you design a building or even a road, you should always ask yourself the question, is the exact analysis of the approximate model of a structure good enough to serve as an approximate analysis of the exact structure? How close is it to reality? You know, I have a very good friend who wrote a book on earthquake engineering. And you know, most earthquake engineering books are not about earthquake engineering, they're about dynamics, structural dynamics. And he has in it the lateral deflection of a 20-story building that have been calculated to 1,000th of an inch. Or, I don't know if an inch means anything to you, but it's 0.025 millimeters. Now, can you tell the difference between 0.02 and 0.04 millimeters in a building? Do you think the building cares? But we do it. We love to make exact analyses of the approximate structure. And the structure model is approximate. Anyway, if you don't agree with me, let me know, and I'll be very happy to concede. Surrender. If you think that your analyses are exact. Look, there was a commercial before we came here, and I would like to put in my own commercial. If you have time, if you read in English, read the article that you can find on the internet, the Faustian and the Magian in the building of a building code. It appeared in the American Concrete Institute International Journal of May 2006. But you can actually plug it in to the computer and something will come up. I think you might find it interesting. And now I'm talking about building codes. You know, what are building codes for? Well, strictly speaking, building codes are to tell you what you don't know. Building codes should never be cheap textbooks. They should tell you what the limits of your knowledge are. Because whatever you do, if you're designing flat plates, or if you're designing a column that buckles, you know certain things. But around it is the not so well unknown. And what's even worse is that the more you know, the more is the boundary at which there are unknown things. And you have to be very careful about that. I'll give you an example to make it come home. But the building code is supposed to do exactly that, tell you what you should not do. Because you know that, don't you? Your instructors must have told you. If you wanted to design something scientifically, true to the principles of science, you can't do it. It's impossible. So you have to base it on experience and experiment. But you can't go further out. May I give you a simple example? Look, take sigma equals mc over I. You're all familiar with that equation, aren't you? Okay, now think of a cantilever beam with a load at the end. That's fine if you're in the middle of the beam. But if you're at the fixed end, that doesn't apply. And that's where you need it. But as Hardy-Cross said, certain things don't fit with the facts, but the results are okay. But don't forget that. Sigma equals mc over I doesn't apply when you really need it. It's irrelevant. But the code doesn't tell you that. We must all be sensitive to the limits of what we know. Let me tell you a story. You haven't seen it. It comes from my time, from the time I was a student. And it's the J factor. Look, I can explain it to you logically, if I can. If I have a building and it is subjected to shaking, right? It shakes in various modes, first, second, third, etc. Now, in the first mode, of course, it tends to bend over like this. In the second mode, it's the other way. In the third mode, then you have two breaks. Am I making sense? Now, surely, the result should be the combination of all three modes. Surely, the second, the third, the fourth should be reducing the effect of the first mode, right? And this was believed by the leaders of our profession. And they invented the J factor, where J, of course, was expressed simply as it should be, was 1 over 2 times the cube root of t. And you can understand that very well. If t is 1, then j is 1/2. So you take the moment that you compute from the first mode and reduce it by 50%. Very good, makes a cheap structure, right? And now, see, this is a perfect case of not knowing what we didn't know. And this was in the code, in the so-called Blue Book. And it was, of course, said to be not more than 1, obviously. Nobody would do more than 1. And not smaller than 1 over 3rd, but that's not important. If you had a frame, the so-called class 1, the business class frame, and you had a period of 1 second, then your base shear for calculating the bending moment became 2/3 of 1 over 20, and then you multiplied it by 1/2 for the J factor. You reduced it by 50%. It's a perfect case of not knowing what we didn't know. Now, the Caraqueños said, hey, the gringos must be smart. And you think gringos are smart too, don't you? You admit it to yourself. So they said, hey, they must know what they're doing. So they followed what the California Code did. And they built many structures. It was a good time economically. And they believed it so well. Hey, let me give you a perfect example of not knowing what you don't know. That, look at this. Look at the change in the size of columns. What does that say? Huh? That says that the engineer who designed it believed implicitly in his computations. Don't ever do that for earthquake engineering. Don't ever do that. Don't ever believe your numbers in that respect. But they did this, and what is more, when they had a 21-story like this one, they used very small corner columns, 25 centimeters, 250 millimeters by 250 millimeters. Hey, do you use centimeters? Because the French tell me, that's gone. Huh? There's no such thing. But anyway, 25 by 25 centimeters because they reduced the overturning moment according to what the people in California reasoned. I mean, even their center columns was like 55 by 55 centimeters. And this is what happened. Fortunately, this building didn't go down, but 3 others did, completely. And because of not knowing what they didn't know. And it wasn't their fault. Huh? They looked to California and said, hey, them cats know what they're doing. Let's follow them. Here's another one. Another one. And I can't show you the pictures of the other buildings because they were completely gone by the time I went there. But it's a perfect example. Now that we're finished with that, let's talk about something else. And I am not being an anarchist, I assure you. I want you to calculate things exactly and do everything the right way. But, you know, Professor Paolo Montero and I were arguing about this. He said the Pope's Borgia were Italian. I said, no, they were Spanish. And we went through a big argument until we were able to look into the internet and find that they were indeed from Valencia. Of course, you shouldn't be proud of it. They were very strange people. But this is attributed to one of the Borgias. He says, Vinci was a nice-looking man. And when Borgia says that, you better beware. Huh? He played the lute. You know the lute? And he sang very well. Besides, he knew how to draw. You know, this is the best definition of engineering that I've ever seen. But it's backwards. That's why I'm quoting this to you. But he decided that he wasn't just an artist, and he wanted to be a practical man. He wanted me, to hire him as my engineer. I hired him, but I wasn't totally convinced that he would be able to do the job. I prefer my engineers to work like engineers and not like artists. Vinci wasn't a real success as an engineer. Instead of what we had on hand, he would ask for better things that we didn't have. You can read that, right? I don't have to translate that for you. Now, this is where the engineering definition comes, and I love it. Huh? He says that, but he wasn't reliable in the day-to-day details of the work. And he made simple problems complicated. You see, if you're an engineer, if you want to be a successful engineer, first, you have to care about simple details, like screwdrivers and nails, what have you. You've got to look at detail, as you would in a car. And you should make things as simple as they can be. Or as Einstein said, no simpler, but as simple as they can be made. Look, you must have heard the statement that if you're going to be wrong, you should be wrong the easy way. And I hate to tell you that, but in almost everything you do, you're going to be wrong, because we don't know everything, especially in earthquakes. So you should make your calculations as easy as possible. The result of the work divided by labor may be optimized, should be optimized. Again, I bring this up to you. but this time in Spanish. You should, if you're going to be an engineer, you should always ask this question of yourself. Let me give you an example that I admire. Nathan Newmark was a brilliant engineer. And he made an estimate of the slip of a dam. Do you realize what a complicated problem that is, the slip of a dam? I mean, if you have a structure like this, sitting on, let's say, soil, how much will it slip in an earthquake? Now, look at what he did. He said, this red chunk models the dam. That's the ground. The ground moves according to y of t with time, and this moves relatively at a different rate. And that's the slip, right? I mean, that, so far, it's exact. See, this happened in my student days, and I remember it well. When he was discussing it, he said, let's assume that this is the earthquake. That's the earthquake, constant acceleration over a period t sub o. As naive as I was, I raised my hand and I said, sir, shouldn't you at least make it sinusoidal? Make it look more like an earthquake? He said, that's dumb, and that makes it complicated. So he assumed the earthquake, the ground motion record that we fight over, to be that rectangle. Now, if that is so, if you look at the velocity of the ground, then it increases constantly at a steady acceleration, and then when it comes to time to, it stops. The red body, of course, is activated by the friction between it and the ground. And usually the friction is less than the ground motion, so it goes up like this. And here they meet together. Now look how simple it is. At time t0, his earthquake stops, because it's one rectangular wave. I mean, it's like a cartoon. At time tm, the dam catches up with the ground, because the ground is moving faster and the dam is trying to catch up. So the difference in these two triangles is the slip. And look at how he calculates it. I mean, even there, it's genius. He takes the area of this triangle, which is very simple, right? It is the velocity, Tm divided by 2, and he subtracts from it that one, which is the velocity, To divided by 2, and he gets this expression. You know, this expression has received much criticism by a lot of very smart people. And they said, oh, this is too simple. But listen, how well do you know the friction? How well do you know the friction in a case like that? How well do you know the ground motion, the PGA? Very approximately. Well, if they're both approximate, if you're going to be wrong anyway, you should be wrong the easy way. And I think of it as a victory of the human mind. You know what? I came across 2 papers in the last 3 years who were criticizing this, saying it wasn't exact enough. How can you be more exact about friction and about the PGA? Well, but it's a perfect example of making things simple. You know, I told you my story of Mexico City. I came to Mexico City the next day, and I went to the embassy, and nothing was wrong. The embassy was hardly touched, and I was relaxed. And the reason we had lost contact with it was that the Pino Suarez building, wasn't it, had gone over. And the embassy communication equipment were on top of this, and I could have committed suicide before I came to Mexico City, and it would have been for naught. Now, here's another interesting thing, and that is probably the most important thing about safety in earthquakes. This was one of the columns that sort of survived at the base of the Pino Suarez. I think you can tell what happened here. No, the wells gave way. I happened to be there with some prominent engineers from California. They looked at it and they said, Mexican workmanship. It'll never happen in the United States. It wasn't 10 years afterwards. In the Northridge earthquake, we had the same problem. And you know, I'm not exaggerating. I was there with a bunch of Japanese engineers. They looked at the American errors in welding and they said, it'll never happen in Japan. 6 months later in Kobe, they lost series of buildings because of welding. But anyway, the point I'm trying to make is not that. That if you're interested in saving lives, if you're interested in life safety, you gotta watch to detail. And you know, in a way, my heart goes to this engineer. Because can you believe if you're in the responsibility of building a 21-story building, can you go and check every effing whale? I mean, effing, but don't forget, between you and the finished product, there are many people, and they all have to do the right thing. And if they don't, it's too bad, because you are to blame. So you have to care for detail. Now, with that, let's go to important things that I think you should know. Really, you need to know 2 rules for earthquake-resistant design. I'm counting how many people are sleeping. So far, I've seen only 3. That's not bad, huh? Considering the circumstances. You need to know only 2 rules, 2 simple rules. The first one is to maintain the elevation of the floors. You don't want this. You don't want that. You want your buildings to be like this and not like those nearby. You want the floors to be at the same elevation after the earthquake as they were before the earthquake. You don't want that. Nor this. But let me ask you, what should you do about this in order to avoid this? Do you have any idea? Is it more careful finite element analysis? No, it is simply tending to detail, making sure that your connections work well, that your transverse reinforcement is in the right place, that your welding is acceptable. But please, allow me to repeat it again. To avoid this, you have to care about detail. It has nothing to do with analysis. Nothing. Believe it or not. Now, the second rule is to maintain the shape. And why this rule? It's because you want to save the investment, the money. You do know, don't you, as Thorstein Veblen, an American economist, said, he said, engineers are caught between the bankers and the reality. And they have to somehow tend to the structure, but they also have to please the bankers. And this doesn't please the bankers. If this happens to your building, you lose the investment, although you save lives. Here again, and this was a very interesting case. This was the Olive View Hospital in Los Angeles, and in 1971, look, it was a simple detail. It had nothing to do with analysis. The frame was filled in by unreinforced masonry walls. Now, that meant that whenever there was a spectral displacement, all of it was concentrated at the first level. Now, the fortunate thing is that, and we'll have to talk about this again, he used spiral reinforcement in the columns. It is something you can't really afford to do anymore. But that saved lives. But more importantly, the equipment in the lab, in the hospital, which was very expensive, came out of it totally untouched. And there was only one fatality, and that was because of something having to do with the oxygen supply. But other than losing the building, there wasn't much damage. And you know what the building costs in terms of what's inside the hospital? 5–10% of the total cost. This building was refreshed in steel walls, steel shear walls. Then came the Northridge 1998 earthquake, and the building did very well, but it shook so much that all the equipment was gone. So this time they lost 90% of the cost. It's hard to be an engineer. It's really very hard. But allow me to repeat, the critical issue for saving lives is not analysis. It's taking care of detail. And taking care of detail depends on experience and experiment. It depends on looking. You don't want that in a building that you design. The critical issue for rule number 2 is very simple analysis. And am I running over my time? How much more time do I have? Another half an hour? All right, and then I'll skip the videos if you want. And I will talk to you about the simple analysis. And let me also try to tell those of you who are sleeping next to you, in about 5 minutes, I'll start something very useful that they will find useful rather than this talk. Thank you. Thank you very much. For example, there was an earthquake in Bonn about 2 years ago, and there was a lot of damage, a lot of fatalities, but why? They were for inadequate anchorage for main reinforcement, or hoops inadequately anchored in shell concrete. These have nothing to do with calculation. Bottom bars not anchored. Top bars extended into the joint, outside the column bars. All, low down detail, but you're responsible for it, and you've got to be sensitive to it. The so-called captive column, which was first observed in Macedonia in 1963. It happened in Japan also. These things don't show their ugly head in analyses. Now, look at this. Of course, first I will admit, to look at something that has happened and to explain this is easy. You should ask me, could you have said this before this event? I'm not sure. I think I could have, but I have to be careful. You think about this. Now, look at this old building sitting up there. You know it hasn't been designed for earthquake. This one has been designed using, even in those days, finite elements, etc. But this huge dome is supported at 4 points. What do you expect? You either put that on walls or you don't put it on columns, right? A column ain't going to do it, because all you have to do is think of this thing turned through 90 degrees, and it's hanging like a sheet on 4 buttons, so to speak. After the earthquake, this old stupid building stands up. This brand new building, elegantly designed, falls out. But the Macedonians had a very simple solution for it. This was an exhibition hall. After the earthquake, they made it an open-air exhibition hall. And that was all there was to it. They just took away the garbage. Okay, now the useful thing. I want to tell you the story of a very simple approach to drift. How to calculate the drift And you know you can't do it exactly because in order to be able to do it exactly, you have to know the ground motion. So it's got to be an approximate procedure, no matter how you look at it. Hey, and you know that, don't you? In engineering, one does calculations in order to compare one choice against another. One never believes that he or she is getting an absolute answer, right? The role of calculation is comparison. It's the story of the University of Illinois earthquake simulator. It's a very simple toy, measuring about 4 meters by 4 meters, and activated by a pump that was sophisticated enough to simulate one component of ground motion. It was really a toy, nothing else. Now, it was built in the late mid-60s, at which time Newmark's opinion of calculating the linear response and dividing it by 4 was the dominant thinking. And the whole idea was when determining the lateral forces. That's what we were interested in. The first series of tests were done on some very simple specimens by Dr. Takeda. He took these, put a weight on top, and put them on the machine. And now listen, you're looking, and you're seeing the force displacement relationship. It isn't linear and then plastic. It is not. But you interpret it as that. And hey, if you're awake, or for those of you who are awake, let me say this very interesting thing. Not only that, but you take this system and you shake it to, say, to a 0.5 G, and you get a deflection of 1. Then you double the deflection, the ground motion, and you get a deflection of 2. But if it is force, then the minute it goes above that point, the whole thing should collapse, right? You can't apply a bigger force, but I'm there and I don't notice this because I'm preoccupied with how to calculate the force. And indeed, that's what my problem was. I wasn't seeing what I was looking at. Dr. Takeda actually produced a wonderful hysteretic relationship for reinforced concrete that is still used in Japan, in Europe, and elsewhere to calculate the response. But our fixation was on how the force was being reduced. It was the Newmark principle. Then comes another engineer. He tests just one-story frames like that. And he finds, and again, thinking Newmark, this is the ductility, the maximum deflection divided by the yield deflection. Actually, it's irrelevant, but anyway, that's what it was at that time, versus what he called substitute damping. The damping that you would need in order to be able to, and I'm sorry, I'll use the word retro-predict, the ground motion. And it was found that as you shook it more and more, the equivalent damping increased, whatever damping is. You know, I've been working in the earthquake business for over 40 years, but I still don't know what damping is exactly. I have to think of it every time. But the substitute damping, I should have seen it right away, but I didn't. Was if you really put an earthquake motion, went from about 2% to about 10%. In fact, look, no matter what happened, the equivalent damping, the apparent damping, was about 10%. You know, what these tests said, and I, dumb, didn't see it, is that if you have even a steel or a reinforced concrete building, and you shake